Hello everyone, today we'll be discussing simplifying radicals, and to get started, let's first talk about what a radical really is. Now here we say the nth root of x is equal to y if and only if y to the n is equal to x. So notice I say nth root, so this is known as a root or index of the radical. Now the radical symbol itself is this kind of division looking thing, but it has that check mark to it. So it's not really division, but it's kind of like division in some sense, because we're kind of breaking up or doing the opposite of this exponentiation, which you could think of as a repeated multiplication. So it's very division-like, but we often think of it as just the opposite of powers, basically. Now, for the purposes of this class in particular, we'll be very often looking at when n is equal to 2. So a lot of the examples I'll be doing are for square roots only, but what I'm about to say throughout applies to any radical, even if the root is not 2. So here, for instance, when you do not write an index, it's assumed to be 2. So here the square root of 5 is the second root of 5. The square root of 144, for example, is the second root of 144. Okay. So what these answers are basically have to do with what power we need to, or what number we need to take to this power to result in the number inside of the radical. By the way, the number inside of the radical is referred to as the radicand. That's not super important though, so I'm not going to write that, but that is a language that comes up every now and then. So now, I'll write out over here a list of squares, and this is one way you can do this. You can just square numbers, if you're taking a look at square roots anyways. So if you square numbers, eventually you'll get a hit somewhere down the line. So let's take a look. So 1 squared is 1, 2 squared is 4, 3 squared is 9, and 16, 25, 36, 49, you get the idea. So we can keep going down the list until we hit whatever we're trying to take the square root of. In this case, for the square root of 25, this implies that the square root of 25 must be 5, because this is taking a look at squares reversed. So the reason why this is true is because 5 squared gives you 25. So this is the reasoning behind that, but at some point, we don't look at the reasoning anymore. But this is kind of the thought process as to why the answer is 5. For 144, we have to go way down the list, and actually the answer will be 12. So again, this is because 12 squared is equal to 144, and it'll allow you to verify that on your own. Multiply 12 by itself, you'll indeed get 144. Now for cubes, because this is a cube root, we need to take a look at cubes. So I guess over here I'll write cubes, and it won't take us long to get to 27. So 1 cubed is 1, 2 cubed is 2 times 2, which is 4 times 2 is 8. 3 cubed, remember, is 3 times 3 times 3. 2 3's gives you 9, and then 9 times 3, of course, is 27. And if you wanted to go one more, 4 to the third, for instance, is 16 times 4, because 4 times 4 is 16, which will give you 64. So this says that the cube root of 1 is 1. In fact, any root of 1 is 1. The third root of 8 is 2, or cube root of 8 is 2. Cube root of 27 is 3, that's what we're being asked here. And the cube root of 64 will be 4, because 4 to the third will give you 64. So again, this is because 3 to the third power, that's our index after all, gives us the inside of the radical 27. And I guess I should box this as well. Okay, so there are a few properties I want to discuss. These are actually the only properties we're going to see with radicals. And one is that when you take the nth root of x to the n, you just get x back. This actually really only works when x is bigger than 0. We haven't taken a look at what happens when you take negatives to powers. That's something we can certainly discuss. As it turns out, when you take a negative to an even power, the negative goes away. But when you take a negative to an odd power, the negative stays around. So if x is negative, for n being even, it would just be the absolute value of that, so ignoring the negative sign. But if n is odd, then the negative remains. But again, for the purposes of what we need to discuss, we'll only consider positive bases. Okay. So now the next property is kind of the reverse of a property we saw from exponents, which was this. So this kind of mirrors the exponent property. Xy to the n is equal to x to the n times y to the n. And we explained why this is true, so if we understand this, then we'll certainly have an understanding of why this is true, because the radical clearly is just the inverse operation of taking a power. Taking something to the nth power, that is. So now here we want to simplify this radical, the square root of 80. Now, if we kept going down the list, we find out that 80 has no proper square root. So instead what we can do is we can try to simplify it by breaking it up into a number times another number where hopefully one of the numbers can be square rooted, and we can apply this property then. And in fact, I'll just kind of tell you right away what the proper one is, and it is 16 times 5. Then we can split it up as the square root of 16 times the square root of 5 using this property. And there's two ways of seeing it. Either we can say the square root of 16 from this table is 4, so this is 4 radical 5, or we can say, well, if you were to split 16 up, it would be 4 squared, because it's of course 4 times 4, and since there is a hidden 2 here in the radical root, radical index of the radical, these cancel out from the first property and just give us this result anyways. And in fact, basically what I'll be doing in the next screen here is we'll be taking a look at some more complicated examples where we can just kind of go overkill in some sense and completely factor the inside. So if I were to completely, just to show you, if I were to completely factor this, it would be 2 times 2 times 2 times 2 times 5. And the reason I know this is because 16 is 4 times 4, each 4 is a 2 times 2 though. So we end up with 4 2's in multiplication and a 5. And because this is technically 2 squared, this is technically 2 squared, if we were to split this up from the first property, the square root of something squared is just that number itself. So in fact, what this really gives us is 1 2 from this pair times 1 2 from this pair times radical 5. So notice whatever is paired up comes outside of the radical as one of those numbers, and whatever is not paired up stays inside the radical, and then we can multiply these together to get our 4 radical 5 answer that we got before. So yeah, I'm kind of going over this a few different ways. The kind of more efficient way is to look for the largest square that the inside can be divided by, square root that, and then whatever is left over inside. Or the overkill way, factor completely, look for pairs, each pair comes out as one of that number. And in general, if you have an nth root, you don't need a pair, but you need an n tuple, if you will. So you need like n many of that number. So for example, if it's a cube root, you need 3 of them to come out as 1. If it's a fourth root, you need 4 of them to come out as 1. So I hope that's kind of making sense. But again, right now we're going to only focus on square roots. So now I'm going to erase this, and in the next screen, we're going to be taking a look at some more advanced examples. We'll be taking, well, basically advantage of these properties and essentially doing what I've done just now here. Okay, so like I said, these are some more advanced examples, and they look pretty ridiculous as you go down the list. They seem to get harder and harder. At least they look more intimidating. But with a little bit of thought, we'll be able to handle them just fine. So for the first one, we'll take note of a few things. The first thing I want to note is 64. We saw in the previous list, the square root of 64 is 8 because 8 squared is 64. So in fact, if we were to split this up, then right away we can see that this is just going to be 8, so we'll get 2 times 8. Now this radical, we haven't actually dealt with variables to a power inside of a radical yet, but it's actually not too bad. There are a few ways to see it, but the way I kind of explained earlier of completely factoring a number totally works here. If we completely factor x to the 5th, notice it's just 5x's in multiplication like this. And if we were to take out pairs as one number outside of the radical, 2x's come out, 1 for each pair. And notice 1 stays behind, so we get this. Now, at this point, all we need to do really is just combine things. 2 times 8 is going to be 16, x times x is x squared, and then we have radical x. This is completely simplified now, and we know this because what's inside of the radical can't be simplified further because we can't factor it. Of course, you may ask, well, what if x is 16? Then you can break it. But the fact that we don't know what x is and there's no obvious power on x, we can't proceed any further. Okay. Now again, if you were to completely factor 64 x to the 5th, 64 ends up being 2 to the 6th. And you can actually go through this with a factor tree, for instance. And you'll get 6 2's in multiplication, and then you'll get 5 x's in multiplication, and you'll clearly see that you get 3 2's coming out outside of the radical. So outside of the radical, you get 1 2 for each pair. And notice 2 times 2 times 2 is indeed 8, so we'll still get 2 times 8. So again, these 3 2's multiplied to this 8 here. This 2 was already outside. And the radical x to the 5th part we already explained, so I don't need to do that there. this one I think I will explain that way and completely expand this out as much as we can. And I mentioned factor tree in the previous problem, so I'll actually show the factorization of 180, in this case, via factor tree. Notice I drew a pretty extended radical here. Okay, so 180, we can factor as what times what? Well, I know 180 it ends in a 0, so it's 10 times the number without the 0, which is 18. Then each of these can be factored. 10 factors as 2 times 5, 18 factors as 2 times 9, or 6 times 3, it doesn't matter, but just keep factoring. 9 factors as 3 times 3. Good. So now the parts we get to that we can't factor further are prime factors. Prime just means you can't factor it more than it is already, besides just 1 in itself. So 2, for example, is just 2 times 1. It's not something else times something else besides just 2 and 1. Same goes for 5 and 3. Okay, so with that being said, these so-called lowest hanging fruit of the factor tree are the prime factors of 180. So 180 is 2 times 2 times 3 times 3 times 5. So let me write that in order. 2 times 2 times 3 times 3 times 5. Okay, good. X to the 8th, we'll have to write 8 x's, I guess, so that's fine. It's 4, 5, 6, 7, 8, and then 3 y's. So 1, 2, 3, excellent. And now what do we know? We know that if we have a pair of a number, then that number comes out, that one number comes out of the radical. So the 5 is already in front. I'll leave the x for when we get to the x's. This says that 1, 2 comes out. This says that 1, 3 comes out. This 5 unfortunately stays behind. And notice for the x's we have 4 pairs. So we have 4 x's coming out. 1, 2, 3, 4, and I'll draw the arrows here again. And for the y's we only have 1 pair, and unfortunately 1 y gets left behind inside of the radical. So now inside of the radical, once we pull all this nonsense out, we have only 5 and y left inside now. So now if we try our best to combine what's on the outside, we have 5 times 2, which is 10, times 3 is 30. We have 4 x's, so that's x to the 4th, and 1 y, and then inside the radical we have 5y. Perfect. Now I did this the complete way by expanding each of these out into their prime factors as much as I can, then grabbing pairs, bringing one of those numbers out of the radical. And that's fine, you can always do that. If you wanted to do kind of a quicker way, well, you'd have to see what's the largest square that goes into 180, and since 2 and 3 came out, this tells me that 2 times 3 is 6. If you bring that back in the radical, you'd have to square it, so you get 36, and there's a 5 inside. So this tells me that 180 is 36 times 5, and obviously it is because, again, 2 times 3 is 6, we have 2 of those pairs. So we have 6 times 6, which is 36 times 5. So if we've written it like that, then we can square root the 36 to get a 6 out. 6 times the 5 would give you 30. Now as far as the exponents go with the variables, if the power is even, you'll have an exact number of pairs with nothing left over. If it's odd though, you'll always have 1 left over outside of the pair, or pairs. But in this case, it's just 1 pair for y. So for example, x to the 8th, since 8's even, you can split that up into 4 even pairs. But for y to the 3rd, 3 is odd, so you'll have 1 pair, but then 1 y left over. So a quick way of doing this is just, if it's even, half the number. If it's odd, 1 stays inside always, for a square root anyways, and then whatever you get after taking away 1, that half that many come out. So for instance here, 3 is odd, so 1 gets left behind, but 3 minus 1 is 2, and half of 2 is 1, so notice the power of y here is indeed 1. Okay. So with that being said, I'm going to try my best now, kind of as a conclusion to this video, to handle this crazy looking problem by kind of witnessing everything we saw. I'm not going to do it the expanded way, but just based on what we just discussed, and for 75, we'll have to see the largest square that goes into 75. Now 75 isn't too hard to see. 75 is 3 times 25, or 5 times 15. But since 5 and 15 aren't squares, that factorization will work. But for 3 times 25, that works. Because since 25 is 5 squared, then we can take the square root of 25 as just 5. So a quick way of doing this is to say this 75 is 3 times 25, and this is just 5 squared. So if you were to break up the 75 as 3 times 25, each of those square rooted, the square root of 25 is 5, so a 5 comes out. And 5 times 3 is 15. So that means this comes out, that 5 comes out, but this 3 stays inside the radical. So that 3 is going to stay inside the radical. Now for the powers, if they're even, just half that and they come out, none are left behind. So the even power for x is 10, the power for x is 10, which is even. So half that, 5x's come out. None left inside. For y and z, those are odd, but if you take away 1 from each of these, 3 from, not 3, but if you take 1 away from them, so 1 from 13 is 12, half of 12 is 6, so 6y's come out. If you take 1 away from 25, you get 24, half of 24 is 12, so 12z's come out. And since they were odd, one of each is left behind, a y and a z. But don't forget that 3 though was left behind because 75 was 3 times 25. So I'm kind of arguing this without really showing too much work, which is nice that you can do that. But again, if you didn't quite follow this, you can always just go this way and completely expand it out. But in that case, it gets a little tedious because you'd have to write x 10 times, y 13 times, and z 25 times, which can be a little bit of a nightmare. But try it on your own, however you want to try it, and you'll see that you'll get this answer regardless. So I really hope you enjoyed this video for simplifying radicals, and I'll see you in the next video. Thanks for watching, and see you then.